So first of all, I would like to thank the organizers for inviting me here and giving me an opportunity to talk here. It's always a pleasure. Wien is a beautiful city and nice people around, many friends. So thank you very much. And what I will talk about is relatively fresh, so it's even not written down yet. So if some people will get interested and will try to ask questions or to check, it will be appreciated so that I will know where the weak points are. So the question I would like to discuss is the following. First of all, a couple of definitions. For definition, so by model domains, I will mean the following model domains. So we are in Cn with the coordinate z cross C1 with the coordinate w. W is u plus iv. And our domain, say, will be omega. Then it calls a model domain if it has the following form. Omega is model if omega has a form z and w in C and z cross C1w such that v is larger than some function, say capital phi of z and u. So phi in my definition is presumed to be continuous. And the whole domain should be pseudoconvex. So if you have pseudoconvex domain with continuous phi, having this form, for me, it's a model domain. Okay, if it has some special smoothness, then it will be added to the definition. So this kind of domains are very common. I mean, in the scaling method or when you study, say, points of finite type locally, you present this in this form, and then you do something. And the question I would like to discuss here is hyperbolicity of this kind of domain. So these domains are unbounded. For bounded domains, the question of existence of Kobayashi metric or Bergman metric is not a question, it's obvious. But for unbounded domains, it's a question. And there are still important open problems in the case of the manifolds, for example, dependence of Kobayashi hyperbolicity with the topology of the domain, stuff like that. And many open questions exist. And this is, for me, the simplest case to try. So the state of the art, up to my knowledge, is the following. So in the case of C2, which is the simplest case, if omega is contained in C1z cross C1w, then in the literature before, there were some results about Kobayashi hyperbolicity for phi being independent on U for rigid domains of special polynomial type, if it's polynomial with some condition. So it was far from being complete, the description. So in 21, I had a paper which gives complete description of Kobayashi and Bergman hyperbolicity for such domains in geometrical terms. So it's published in Mathematische Annalen. And then the answer is the following. If you have model domain in C2, then the property of being Kobayashi hyperbolic, Bergman hyperbolic, meaning that there is a Bergman metric, Brody hyperbolic, always holds true except for one very exceptional case. The case is that the boundary of the domain is foliated by graphs of entire functions. And actually, there is only one entire function. You have to take the graph, and then the other graphs are just the translations. So this is the only bad case. If you have model domains which has some other form, not of this form, then it's always Kobayashi hyperbolic, Bergman hyperbolic, and have a lot of nice properties. In the case of higher dimension, if here you have not C1 but C2, the equation is much more complicated. And we had an example in our paper with Arvegas. Well, then there is some more term. I will probably not define it here. We have studied it for years. The notion of the core was also involved in the description. And then in the case of higher dimension, in the case of C2, there was a relation to the core. In the case of higher dimension, there is no relation. They might be non-empty core, but still Kobayashi hyperbolic. So the situation becomes much more complicated. And it was not even clear how to pose the hypothesis, what might be the description. And then last year, there was a conference in Bochum, and Stefan Nemirovsky suggested to consider the following question, which turns out to be a nice question. Namely, assume that you have domain like Z in higher dimension, and assume that this domain is strictly pseudoconvex. Okay? Does it follow that it's Kobayashi hyperbolic? So strict pseudoconvexity, it's a local property. This is the problem. I mean, you have some local property, and you want to get some global consequence out of that. How to transform this local property to the global one. So I don't know how to do it in that generality, but what I can do now is the following. I will try to explain you the solution to this problem in the case of rigid domains, when it does not depend on you. Okay? Then I claim that the domain will be Kobayashi hyperbolic, and it will have a Bergman metric. And I do not mention the whole literature. I mean, there are tons of literatures about the Kobayashi and Bergman hyperbolicity, in particular domains of this type. Takeo had a paper with Buyen Chen and with someone else about completeness of these domains with some extra conditions. Let me not mention this. I will try to explain the idea how to prove. Okay? So let me state the theorem. Let omega be a strictly pseudoconvex domain, model domain, model rigid. Rigid, once more, means that it doesn't depend on you. Rigid domain in ENZ cross C1W, n is larger or equal to 2, then omega is Kobayashi hyperbolic, and possesses a Bergman metric. So I will actually work in more special case, namely in the definition of model domains. We assume this function to be just continuous. If our boundary is strictly pseudoconvex, then I even can assume that it's the boundary is smooth, and it's due to Rydberg smoothing procedure. It's easy to arrange for these domains. So it's not an extra restriction if I will work with smoothly bounded domains. So let me explain the main idea and then the main problem and how to overcome over this problem. So the main idea is the following. Let me make some pictures. This is RV. This is RU. Here we have C and Z. So we have a graph. And it's a rigid domain. So in U direction, it's just a translation. It's invariant in U direction. Our domain, I have some chocks here of different colors. So the domain omega is above. So this is omega. And the first thing I would like to do is the following. I will exhaust C and Z cross RU, but by some ellipsoids. So I take R positive, epsilon positive, delta positive, and I will take a ball of radius R in C and Z, and I will take an egg, not of radius R, excuse me, radius R minus epsilon. And here the size will go to infinity. So say R divided by delta, something like this. Epsilon and delta will be small, will be taken small. So if epsilon positive, delta positive, and z tends to 0, then my egg will become, at the end, like an infinite strip. And here I will exhaust the ball of radius R. So this figure I will denote it by something like G, R, epsilon, delta. Then over this domain, over the boundary of this domain, I take my function, which defines the boundary, this function. Then I will do the following. I will use the parent method, but parent method not to pluri-subharmonic functions, but to functions defining the strictly pseudoconvex graphs. So I will take, I have many chocks here, I will use this. I will take graphs, a family, say F, is the family of functions, say F, smooth, say C infinity, in the closure of this domain, such that V is larger than F of Z and U is strictly pseudoconvex. Strictly pseudoconvex on this part of the boundary. Strictly pseudoconvex, by this I mean that the part above larger is strictly pseudoconvex. And then I take the soup over at any point for any Z in my egg. I define the function, say phi, this function was phi R epsilon delta at the point Z is supremum of F of Z for F in my family. So family is also depending on this R epsilon delta. So I just take the supremum. I will get something. This something is known to be continuous up to the boundary. It's an easy argument. It's more or less like in the Walsh paper for plurisubharmonic continuity of plurisubharmonic functions. In the case of C2, it was explained with some estimate on the model of continuity in my paper in '93. In the high dimension, it's the same argument, actually. So you will get something continuous, and the picture will be, so here you have your initial function, here you have something which is larger, in principle, larger or equal, and the whole domain still is pseudoconvex. Because here you're taking soup over functions defining something strictly pseudoconvex. The soup will define pseudoconvex. Here you might get a corner, but it will only make your pseudoconvexity better. So now, my function depends on z, and my function f depends on z and u. Depends on z and u. Excuse me, I correct. This is important, and then I will answer. Yeah, this also depends on z and u. Correct. This is correct, and for any u. For any u such that z and u are in this domain, in this domain. This is correct. Yes, please. This does not depend. This is an egg. This is an exhaustion. F is a function which is smooth on the egg. Yes, one more thing is missing. So this function is lower or equal than the given function on the boundary, like always in parent method. This is correct. So phi f is less or equal than phi on the boundary of G. Yeah, this is correct. This function will depend on u, but what I will do now is I will make an exhaustion. I will, with fixed R, I will consider the family of all such domains when epsilon tends to 0 and delta tends to 0. So the egg will get longer, and it will exhaust the ball of radius R from inside. And then one can see immediately that if the egg is larger, then because of strict pseudoconvexity of the given boundary data, the solution on the common domain of the definition will be larger. There is monotonicity. This first observation. The second observation, if you have some egg, fixed egg, and you move it in the u direction, when you can take so large egg in your family that it will contain both. It means that at the end, your solution, when you take supremum over all x, will be a rigid function, will not depend on u. Okay? And this is the function I will work with, actually. Okay? So what this picture has, how this picture is connected with hyperbolicity and existence of the Bergman method. I mean, this picture is completely geometric, but it has something to do with hyperbolicity and with existence of Bergman metric. And here I will use two references. One is a result by Nassim Siboni. It's an old result, and it says that if you have a manifold, any complex manifold, and if you have a bounded, strictly plurisubharmonic function on this manifold, then the manifold is Kobayashi hyperbolic. The observation is easy. I mean, it's easy to get, but it was a brilliant thing to see this, to find the observation. So this is the first remark, the first result I will use. The second result is due to Buyan Chen and his advisor Chang. And the result says the following, that if you have pseudoconvex domain, and there you have bounded strictly plurisubharmonic function, then the domain is Bergman hyperbolic, meaning that there exists a Bergman metric. So in both cases, it boiled to the question of existence of bounded strictly plurisubharmonic function. And this is something that I'm more familiar with. I'm not an expert in Bergman metric, but about the plurisubharmonic function, I can say something. And therefore, this is what I'm going to prove, to explain to you that for these domains, there exists a bounded plurisubharmonic, strictly plurisubharmonic function. And due to these two references, it will close the question. My theorem will be done. So how to cook up plurisubharmonic function and what is the dependence to the geometry of the domain. So let me maybe, I don't know if this picture is overloaded or not, but maybe I will try to make it on this picture anyhow, and if it will not be clear, I will repeat it. So what I would like to do is the following. I would like to, so I have this solution of the parent method. I have my initial graph. And my initial graph is lower than this one. It's because, for example, this in the family. So there is a space in between. This space in between, so it's a set of all points over here, which are in v direction above the given function and below this solution to the parent method. So I will denote it by something. This domain is U, and then it depends on R, epsilon, delta. Now, what you can do is the following. So it was constructed for some special egg. You take, say, larger egg, any egg which is larger, and I will consider a compact set now. Compact set will be the following. So over this space in between, it's bounded above by the graph of a given function, phi. Over this egg, it's bounded below by my solution to the parent method. And then over the larger egg, I will consider the cylinder, just this egg multiplied by v direction. And I will cut it by some constant far away above. So my compact set will be Z. And I'm claiming that this set is polynomially convex. Polynomial convexity is easy to observe because here you have even strict convexity, here you have linear bound, here you have strict pseudoconvexity, and this is got by the parent method from something strictly pseudoconvex. So it's an easy exercise to show that this compact set is polynomially convex. Then there is a result, it's also mentioned and proved in the Stout book, that if you have a polynomially convex compact set, then there is a plurisubharmonic function globally defined, which is 0 on the compact set, positive on the complement, C infinitely smooth, and strictly pseudoconvex in the complement to your compact set. I take this function. And if I can exhaust the whole of my domain by these sets, I just take this function, multiply by some little positive constant, and sum up. And it will give me a strictly plurisubharmonic bounded function on the whole of the domain. So the only question is, if you take the union of these guys, shall you get the whole of the domain or not? This is the question. Because if you will get the union, the whole of the domain, then using this function from the book of Stout, using this exhaustion, you cook up the function. easily. So then what it remains to show is, shall you exhaust by this domain the whole of the domain or not? And now I'm coming back to my remark that the function is bounded because take the function from the Stout book. It is 0 here, globally defined in the whole of Cn. Positive on the complement, smooth and strictly plurisubharmonic on the complement, here is 0. It's not bounded, but I need it, it's bounded here. And then by multiplying on a small constant, I can make it arbitrarily small on this set. And if I can exhaust the whole of omega by these sets, I just take a sum of this function multiplied by proper choice of epsilon positive, and it still will be bounded and strictly plurisubharmonic. Is it fine or not? Do you agree? Okay, so. Well, the general statement by Stout is the following. Oh,
this has been known for a long time.
yeah, sure. One can make it by hands directly from the definition. It's just the fact that yes. Well, here you have a little bit more. You have smoothness, but you can do it by hands. So before finding the reference in the Stout book, I did it by hands when I explained to the students. I mean, you take the definition of polynomial convexity, you work a little bit, and you will get it. Good. So what is my question now? My question now is the following. So if I have R fixed, if I have epsilon and delta tending to 0, then my solutions will at the end give me something which is rigid. I explain why. Yes, please. Here. No, because I did not tell it, but because of this, you see, I have some space here, and you didn't ask me why, but I can explain you why. Because here you have 0, in particular, on this part is 0. So if I extend it to be 0 everywhere, I still will get plurisubharmonicity. And this was the reason for me to have this color so that I keep smoothness and everything is fine. So my function will be non-zero, will be positive only here. Okay, and then I can sum up. Good. So once more, if I take epsilon and delta, which tends to 0, I will get something rigid, something which doesn't depend on U. So my question actually is boiled to the following question, which is a question about the plurisubharmonic functions question. So you have phi, which is say C infinity smooth on the whole of Cn and strictly plurisubharmonic in the whole of Cn. So now I have only Z coordinates, C and Z, and here I have something which is strictly plurisubharmonic. I take the ball of radius R in the center, let's say the origin in the Cn, and now I solve the Dirichlet problem for Monchampère with a zero right-hand side. So it's also the parent method, but now you use pluri-subharmonic functions instead. So you will get some solution, and you will get the space in between your solution and the given function. This is my domain now. Question: if I increase the radius, you obviously have monotonicity, so the solution will be larger because you have strict pluri-subharmonicity. The question is, shall you have infinity as a limit? Shall you exhaust the whole of the domain? If you do, then you also exhaust here, and then you're done. In the case of n equal to 1, this is obvious. Why? Because if you do not exhaust, you take the limit, it's a harmonic function. You take harmonic function, this harmonic function, minus this strictly subharmonic function. It's a negative strictly subharmonic function on the whole of C. By Liouville is constant. It cannot be strictly subharmonic. So the question in dimension 1 is easy. In dimension larger than 1, the problem is that you cannot subtract. I mean, you will lose the property of being pluri-subharmonic. It's no linear problem. You cannot do this. So the question seems to be easy, but it was for some period not clear to me how to attack, how to do, and how you can use this strict pluri-subharmonicity local property to get something global. And here, at the end, I found some argument, and I will present it now, and it uses theory of Poletsky about holomorphic disks. So it turns out to be very efficient here, which was a surprise because it's a very beautiful theory, but I knew very little examples where you can use it. So then this will be one more example. And I will not give references. I mean, there are a lot of references about the Poletsky theory. For example, Bu and Schumacher have done these results at the same time. And then Rosé has proved it for the case of manifolds. Then Franz with Barbara has generalized it for the case of spaces. And recently, like a couple of weeks ago, Florian Bertrand with Kuzman have posted the article about almost complex case. They have done it already 10 years ago, so I don't know this time if it's fine or not, but at least it is in archive. I mean, there is a literature, big literature about that. Let me remind you briefly what Poletsky theory is about, okay? So I will not make it in the full generality, but I will make it in the setting which is good enough for me. So say that you have a ball in Cn, and say that you have any continuous function on the closed ball. F is continuous on the closure of the ball. Then what you can do the following. The first thing you can do, you can consider pluri-subharmonic functions. Well, more or less the same kind of family. You consider the family, I will put tilde because the setting is slightly different, is the family of functions which are, well, it's enough to take smooth on the closure. You can even take strictly pluri-subharmonic in the closure. In the closure meaning that it holds true in some neighborhood which depends on function. Such that P is less or equal than F on the boundary. And then you define say F star below at Z, it's a supremum of phi of Z over your family. So you just use the parent method, not on the boundary, excuse me, on the whole of the, it's important, on the whole of the ball. So it's below the given function everywhere, and then you take supremum. So I will make maybe a picture like that. Then you will get something which is obviously plurisubharmonic. It might coincide with the given function somewhere. Somewhere it might be below, but you will get something. You can also play some other trick. You can do the following. You take any disk, immerse it holomorphically in the ball, disk delta. And then you take the boundary value over this disk, which are defined by your function f. And you take the mean value at the center. And then for the given point in the ball, you take all possible embeddings of disks, and you take infimum. And what Poletsky is saying is that this new function, which is defined by disk, will coincide explicitly with that function. Okay? So this is the statement of the theorem by Poletsky. Good. So now I would like to use that, and therefore I will work with the disks embedded. So my problem is to prove that this function tends to infinity. So I need to get somehow some estimate. And to get some estimate, I better use disks instead of using plurisubharmonic function. This is the idea at this level. So I take any disk here, delta. In this setting, it does not need to be, well, it can be also taken inside the ball, but in principle, I can also take disks, just immerse it into the ambient space. So the point, the center of the disk is fixed. I evaluated the given point. And I would like to show that then when R tends to infinity, my function, which depends on R, will tend to infinity at the given point, at the fixed point. So I have a disk. I have my function. To use Poletsky's theory, I need to have some function f. So this is my next step. I will create some special kind of function f. And the special kind of function f will be as follows. So I have a ball here of radius r, centered at the origin. I have my initial function phi, depending on z, which is smooth and strictly plurisubharmonic. I do the following. I take on the boundary of the ball, and outside of the ball, my function will be capital phi. Inside of the ball, I want to get some function which is strictly concave, like that, having the same boundary data. And that's it. So strictly concavity will be important for me in later on when I will work with that. This is easy to get. How you get this? So the question is here, how to get here. So you have the ball, you have your function on the boundary of the ball. You take this set on the boundary, this graph of the boundary, and you take a convex hull. Convex hull, because of strict convexity of the ball, it will have two parts. It will have upper part and lower part. So you take an upper part. It's still not enough strictly convex, But what you can do, you can say this function is, I don't know, f plus, because it's in the direction up. So you take f plus, on the ball you always have a function which is r square minus mod z square. So you add it. This function is already strictly concave, not smooth, but if you want to have it smooth, you use the Ricberg procedure, and you will get it smooth with the same boundary data. So this way you will gain some function like that, strictly convex. And now to this function being given function strictly plurisubharmonic here and strictly concave here, I use the Poletsky method. So here, of course, I will get the same because of strict plurisubharmonicity. Here, I will get exactly the solution of the parent method for plurisubharmonic functions. So here I will get my function. And what I would like to use now is that if I will take disk here and use other procedure, then I can adapt my disk to get almost the same value as here. And then I will study this disk. I will correct it. I will correct it in such a way that it will become properly immersed into the ball. And if it's properly immersed, the point Z0 is fixed, the radius of the ball will get larger and larger. So the size of the disk will be large if you normalize it here by 1. So what you will get, and then on this disk you can restrict our plurisubharmonic function phi, which is given here, for example. In my case, my rigid case, it's strictly plurisubharmonic. So I restrict it to this large disk. Because of strict plurisubharmonicity, because of normalization, you have in some neighborhood, fixed neighborhood, you have positive Laplacian. And then by Green formula, you see that if you have it's an easy observation, if you have a disk, here you have some positive mass fixed. Then you use Green, the integral of the normal derivative is the integral of the Laplacian. And then you integrate once more with respect to the radius, and then you will get that the mean value minus the value here is a double integral where the Laplacian is involved. And when r tends to infinity, then it will tend to infinity, meaning that the mean value and the value at the point will tend to infinity. And this is exactly what we need, because if I apply this to the given function, for my disk, which is properly embedded here, which is large, because of this estimate, I will get the difference in Poletsky disk minus the value of the given function phi tending to infinity, meaning that my function will tend to infinity. So the only thing I need to do is to correct the disk, to cook up from this disk properly. This disk is not embedded in general, it's immersed, I think, but it's in general position, has only transversal intersections. So I need to approximate it by the global disk, also immersed with the boundary, on the boundary of the given large ball. Good. And now how this picture comes to the... Yes, sure.
Why do you have
You take infimum over infimum of the main value. Yeah. I need that, but I will work with some disk. I will take some fixed disk when R is fixed. I will take some fixed disk which almost realizes function. And then I will work with this fixed disk, of course. So I need to correct the disk. I would like this disk to stretch up to the boundary. Remember my artificially prepared function. So if the disk comes out at some place here, then the boundary data is always here. In particular, the boundary data is above this guy. And therefore, the disk cannot go lower. It's a harmonic disk. This function is purely subharmonic. In particular, on the boundary of the disk, I have the value larger or equal than the boundary data. So I just can throw away this part, make on this part value given by the boundary data, and I will get even better. I will get down. The remaining part is still simply connected, because for the disk, it's impossible that you have holomorphic disk and some bubble comes out. It contradicts the maximum principle or continuitetzac if you want. So if you have a disk, then the preimage of what is contained in the ball is simply connected. So it still will be a disk. So this is fine. This way I will cut this part. So what I can do with this part, so with this part I have something simply connected. But remember, I have prepared my function to be strictly concave here. And this for the reason, because what I do now is such disk can be always approximated by the properly immersed disk, and this is easy. I mean, this disk is defined, you have a unit disk, you have holomorphic functions. If you are in CN, you have n holomorphic functions from the unit disk here on simply connected domain. You use polynomial approximation, for example. And polynomial approximation is properly immersed into the whole space. So in particular, you take intersection with the part which is in the ball, and this approximates your disk well. Now you have to compare the value here for this new disk and for the old disk. But look, for the old disk, you have taken the value at this part. For the new disk, you will take value here. Of course, this part is lower than this part. So if you use that, you can only get lower. Therefore, you will gain a properly immersed disk. In particular, this disk will get large when R tends to infinity. You can use this argument, and you see that your function tends to plus infinity. And this finishes the proof. And I'm exactly in time, so thank you very much for your attention.